Every time you zip a file, the same information takes up less space. No data is deleted, nothing is removed. The file becomes smaller, but everything is still there. So how does that actually work? A standard zip file uses a compression method called DEFLATE. DEFLATE works in two stages. First, it finds repeated patterns in your data. Then, it stores the remaining data as efficiently as possible. The first stage uses an algorithm called LZ77, developed by Abraham Lempel and Jakob Ziff in 1977. Here's the basic idea. As zip reads through your file, it keeps track of the data it has already seen. Whenever it comes across a sequence that appeared earlier, instead of storing that sequence again, it stores a small reference to the first occurrence. Imagine a document that contains the sentence, "The lights turned on." A few lines later, the exact same sentence appears again. Instead of storing the entire sentence a second time, zip stores a tiny reference that essentially says, "Reuse line 3. Behind the scenes, that reference is stored as just two numbers: how far back the original sequence is, and how many bytes should be copied. Those two numbers usually take much less space than storing the entire sentence again. The more repeated patterns a file contains, the smaller the compressed file becomes. This also explains why compressing an already compressed file usually doesn't do much. Formats like JPEG, MP3, and MP4 have already removed most of the repeated patterns, so there's very little left for LZ77 to find. After removing repeated patterns, DEFLATE moves on to its second stage. This stage uses Huffman coding, a form of entropy coding invented by David Huffman in 1952. But before understanding Huffman coding, we need to understand one more idea. Entropy simply measures how unpredictable information is. A file with lots of repeated or predictable data has low entropy, making it easy to compress. A file that looks completely random has high entropy, leaving very little room for compression because there are almost no patterns left to exploit. Now think about written English. The letter E appears far more often than Z. The word D appears constantly. The word xylophone appears much less often. Yet in normal storage, every character usually gets the same amount of space. Huffman coding changes that. Common symbols get shorter binary codes, while rare symbols get longer ones. So when a letter like A appears much more often than Z, A gets a shorter code and Z gets a longer one. Since common symbols appear again and again, those shorter codes save bits throughout the file. The result is the same information stored using fewer bits. But if compression keeps saving bits, what stops us from shrinking every file to almost nothing? It turns out there is a fundamental limit to how much a file can be compressed without losing information. This idea comes from Claude Shannon's source coding theorem, one of the foundations of information theory. It tells us that every piece of information has a theoretical minimum average number of bits needed to represent it perfectly. Modern compression algorithms can get surprisingly close to that limit, but they can never go beyond that limit. Here's why. Imagine there are only 4 possible 2-bit files, 0, 0, 0, 1, 1, 0, and 1, 1. Now suppose someone claims they've invented a compressor that makes every file smaller. That means all 4 files would have to fit into just 2 possible 1-bit outputs, 0 and 1. But that's impossible. 4 different files simply can't fit into only 2 unique outputs while still being perfectly recoverable. Sooner or later, 2 different files would have to share the same compressed output. And if that happened, the computer would have no way of knowing which original file to restore. That's why no lossless compression algorithm, not zip, nor any future invention, can make every file smaller. Some files simply cannot be compressed any further. So when you zip a file, nothing disappears or gets lost. The file simply finds a more efficient way to represent exactly the same information.